Evaluating a composition of a trigonometric function and an inverse trigonometric function. And notice on this one, we don't have sine and sine inverse or cosine and cosine inverse. So there's not going to be any really nice simplifying down and just canceling out in this case. So one thing that stands out to me is we have the inverse functions on the inside. So identifying that from the beginning helps out on how to approach this problem. So what I'm going to do is whenever that inverse function's on the inside, I always like to start with a let statement. And I'm going to go ahead and say, I want to define theta, some angle, to equal whatever's on the inside. So theta is going to be sine inverse of 7/9. What that allows us to do is, instead of thinking this is something super complicated looking here, cosine composed together with sine inverse of 7/9, this is really just cosine of theta is like what we would like to evaluate, where theta is defined to be the sine inverse business. All right, so I've replaced the sine inverse, everything on the inside here, with a theta by my definition from my let statement over here. The next thing I'm going to do is go ahead and rewrite this instead of in terms of sine inverse. Let's rewrite this in terms of sine. So if theta is equal to the sine inverse of 7/9, that means that sine of theta is equal to 7/9. Basically applying a sine function to the left-hand side and a sine function to the right-hand side. When you apply it to the right-hand side, the sine and sine inverse composed together are going to get some nice canceling out. From here, if we know that sine of theta equals 7/9, we can draw a quick right triangle. Because we know about SohCahToa that sine is defined to be opposite over the hypotenuse. So we can start labeling the sides of our triangle. The opposite side from where I wrote theta is going to be over here on the right-hand side is going to be 7. The hypotenuse across from the right angle has to be 9. And then from here, our end goal is going to be find cosine of theta. Well, I know cosine of theta, again from SohCahToa, is defined to be the adjacent over the hypotenuse. Well, I know the hypotenuse is going to be 9, so we can fill that in. But we need to do a little bit of work and find our adjacent side. So I'm going to call my adjacent side A down here in our triangle. Well, being it's a right triangle, we're allowed to use the Pythagorean Theorem. So we can say a squared plus 7 squared equals 9 squared. Now that we have this equation that has some constant and just has a squared over here, let's do some solving down and get a squared on one side by itself. So 7 squared is going to be 49. 9 squared is going to be 81. We'll subtract the 49, move it to the other side, make this into a power equation. So we get a squared equals 81 minus 49, leaves us with 32. And then we'll apply a square root to both sides to isolate the a on one side by itself. So we have the square root of 32, which we could think of as 16 times 2. I'm using 16 as a factor because it's a perfect square that's a factor of 32 and the largest perfect square that's going to be a factor of 32. With a little bit of reducing down, we can think square root of 16 times the square root of 2, which works out to be 4 times the square root of 2. Finally, to finish this up, let's go ahead and fill that in. That's our adjacent side length is 4 times the square root of 2, can go up here. And there we have it. That's our cosine composed together with sine inverse of 7/9. An exact answer to go on here, 4 times the square root of 2 all over 9. All right, I hope this helps out. When you have the inverse function on the inside, do the let statement, draw the triangle. You got this. They're not that bad, but it takes practice.